Hello, my name is Michael Miljanovich, and this is an introduction to the internet. Let's start by talking a little bit about where the internet comes from. For most of the people watching this, myself included, we don't really know what a world is like without the internet. We haven't really seen that. But what did things look like way back when, before they had this kind of technology? Well, if you go all the way back to the 1960s, we can start off looking at the year 1961 and look at a guy named Leonard Kleinrock. Kleinrock is a theorist, and his work inspired the idea of breaking up messages into smaller parts called packets. And the idea behind this is that without needing to wait for an entire message to be sent, putting together the whole thing and sending it as one giant item, instead you could break down a message of whatever kind you wanted into smaller components and then send each of those one at a time. If we move forward into 1964, we can use this in the application of military nets. So, independently of Kleinrock and another UK scientist named Donald Davies, who was thinking of this literally at the same time, Paul Barron was trying to make a military communication system that could handle damage from nukes in the Cold War. Suppose you had a telephone line that's set up between three different stations, and the station in the middle gets hit by a nuke. Suddenly your whole communication line is down. You're in huge trouble. So if you want to still be able to send messages, you want to be able to do something a little bit smarter than that. And the name packets actually comes from Donald Davies, the UK scientist, whose work was noticed by ARPANET developers, although they originally sought this information from Barron. So ARPANET is the first packet switching network. Until this point, communication networks relied on something called circuit switching, which is basically what you would think of a telephone system tends to use. Not cell phones specifically, but the wired telephones from way back when. The first message that was sent on ARPANET was supposed to be, just neat trivia, was supposed to be log in, but it crashed after they sent the O, so officially the first, you could consider the first internet message ever sent was LO, if that's it's a little funny note. Anyway, in 1969 was the first ARPANET node actually operational, so the idea behind ARPANET came from 67, and in 69 they actually set it all up. And then in 1972 they had a public demonstration here. We actually got it to work. And NCP, Network Control Protocol, is the first host-to-host protocol. So this is the predecessor to TCP, which is what we use today, and we'll discuss that a little bit later. But the idea behind NCP was to use port addresses to make two connections for two-way communication, so you can not just send messages but receive them as well. The very first email program was called Send Message, SNDMSG. It was used in 1971 to allow messaging over ARPANET, appending the system's host name using the @ sign, so you can kind of see how Twitter may have had some inspiration from that. And so if you want to look at what ARPANET looked like in 1972, it had 15 nodes, and here's a little diagram right down here of the original ARPA network, and how it's basically just these little circles that you can see here, this one, this one, this one, this one, are all universities in general. Unsurprisingly, technologies are coming from different universities, and so this is sort of the connection between, there's probably a better resolution that you can find somewhere of what this network looked like, but it's just direct connections between the universities that were working on this network at the time. So now that we've reached the 70s, we'll talk a bit about internetworking, proprietary nets, new networks, things that are going on around this time. So in 1970, AlohaNet began, the satellite network in Hawaii, which is the first publicly demonstrated network. It uses what's called the Aloha protocol, which is something we still use today. The idea being that you can send packets at any time you want, and an acknowledgement is transmitted if it was received correctly. Otherwise, obviously, no acknowledgement is sent. If there is no acknowledgement, there's no guarantee the thing was sent properly, then what happens, it'll wait a random amount of time before sending again. And this is called random access protocol, the idea that you just randomly decide, okay, it sounds like they didn't get it, let's try again, maybe this time they'll receive it. Cerf and Kahn are the co-inventors of TCP/IP, the internet protocol. And the idea behind this is that if you have a bunch of different systems that all are going to be working together, you want them to be able to network with each other without having identical hardware and software on all of them. It's kind of useless if you need to be the person who designs every single device in order for them to communicate with each other. You want to have some kind of architecture that lets you connect networks even if the devices are not even made by the same person, for example. After this, in 1976, we have Ethernet, developed at Xerox, and Ethernet was inspired by AlohaNet, and is a standard for short-distance communication. You probably have an Ethernet port on your laptop if it's a big enough laptop. In the late 70s, we start seeing some proprietary architectures, things like DECnet, which is short for Digital Equipment Corporation. SNA is an IBM network, XNA is a Microsoft network, and so basically the companies are starting to get in on this idea of, hey, maybe this internet thing could be worth some money. Moving along in the late 70s, we also have the idea of switching fixed-length packets, the precursor to asynchronous transfer mode, or ATM. And the idea here is that when a link receives data with different size packets, small packets have this issue where they have to deal with the queuing delays created by large packets. So instead, why don't we make them a consistent size? Seems like a simple and good enough idea. And then by 1979, ARPANET, which started out with our the little tiny diagram that had 15 nodes in the previous decade, ended with 200 nodes by 1979. So going back to these guys, Surf and Khan, they created a series or a list of internetworking principles. These are the principles behind the idea that my computer right now, which is probably somewhat different than the computer you're watching this on, is still able to connect to networks and communicate with each other. So some of these principles are things like minimalism, autonomy, not needing to make an internal change in order to connect these networks together, trying to create a best effort service model to make sure things are as clean as possible, stateless routers, decentralized control. This one's really important. You do not want to have one person who can just decide, oh, I get to choose whether the internet is working today or not. Not the best approach for that. And really, these principles are still things that hold true to today. These define what the internet architecture of today still looks like. So now that we've reached the 80s, we have some new protocols, a new proliferation of networks, and some other things that I'm going to talk about. In 1983, we have the deployment of TCP/IP, Transmission Control Protocol and Internet Protocol. The migration of ARPANET to use TCP/IP from its original protocol was officially completed on its flag day in January 1st, 1983, which is when these new protocols were permanently activated, and we still use these things today. In going back a little bit to 1982, we have SMTP email protocol. So this is Simple Mail Transfer Protocol, which is one of the protocols that we use today for sending emails and receiving emails. Back in 1983, we also have DNS, defined for name to IP address translation. So DNS you can think of as the phone book of the internet. If you know someone's name, you want to look up their number, DNS is the system, domain name system, which tells you for this name what is the IP address number that you need to access their system. In 1985, we have FTP protocol. This is file transfer protocol, so this is what we use to send files from one system to another. And in 1988, we have what's called TCP congestion control comes out. So this is limiting the total number of unacknowledged packets that you can send from one at a time. If you remember from before, we were talking about how when you send a packet, you want to wait for an acknowledgement so you can send the next one, and so on and so forth. If you don't receive an acknowledgement, you randomly wait and then send a new one. Well, what happens when that number starts to grow and grow and grow? So the idea of a congestion window is to limit how much can be going on before you decide maybe we shouldn't have so many unacknowledged packets being sent in this series. So sorry, let me fix my picture over here so you can see. New national networks are coming around at this time: CSNet, BitNet, NSFNet, Minitel. These are all networks created by countries now, so governments are starting to get interested in this idea of, hey, maybe we can be using this internet too, not just these private entities. And so by the 1990, which is when I was born, we have 100,000 hosts, 100,000 end systems connected to a confederation of networks. The internet is becoming a real thing here. So now that we've reached the 90s, we get into the commercialization of the internet, the web, new applications, and other things that are happening around this time after I was born. In the early 1990s, ARPANET is decommissioned, and it's replaced by the National Science Foundation network, NSFNet, which transitions the world from using ARPANET to the internet that we use today. According to Wikipedia, the linking of commercial networks and enterprises by the early 90s marked the beginning of the transition to the modern internet from the old things that we were using before. And so in the early 1990s, we have the World Wide Web. It's the reason that when you type in a URL, sometimes it'll start with www dot. And what came along with this? Well, we have hypertext. If you want to be able to use the World Wide Web, generally you want to be able to click on a link that will take you from one place to another. And a hyperlink is something that's built into hypertext. In addition to that, we have HTML and HTTP by Tim Berners-Lee. Tim Berners-Lee is what most people would consider to be the inventor of the World Wide Web, the person who made it so that we can load up web pages. HTML is used to write the web pages. HTTP is used to communicate about them. So a full website might be http://www.google.ca. For us, we usually just end up typing the google.ca, and our browser sometimes will take care of the rest of it for us, but that's the full list of the characters that you need to get things going. In addition, in 1994, we start seeing some internet browsers, Mosaic, which is something I never used, and Netscape, which I did use, and then later on we obviously saw a bunch more, but Mosaic browser is probably considered the one that popularized the internet, so that more than just people at government places and businesses and scientists were using them, so the actual average person can access the internet. And in the late 90s, we have the commercialization of the web. So we start seeing things that people might recognize, applications for instant messaging. MSN Messenger started in 1999, ICQ Messenger 1996, peer-to-peer file sharing. So this is where Napster comes in 1999, which is the subject of a whole big fiasco, which you may want to read up on if you're interested. BitTorrent came out in 2001, and so on and so forth. And so this is where people start thinking about things like, well, what about security? We didn't really consider that when we were developing the internet. And so that becomes a major issue around this time. And by the late 90s and the early 2000s, which is when I think most people watching this video were born, we got about 50 million hosts, 100 million plus users, starting to get into crazy numbers where the internet is really taking off. And the backbone links, the things that are making sure the internet still works the way that it should, now are running at gigabits per second, instead of much slower rates that we used to be focused with. So what do things look like from 2005 up until today? As of 2016, 5 billion devices were attached to the internet. As of 2020, according to data from Internet of Things Analytics, 7 billion devices are attached to the internet. I'm sure that number is probably even higher by the time of recording this video, but that's a conservative estimate. This includes smartphones, tablets, laptops, any of that kind of stuff. At this point, we have aggressive deployment of broadband. If you're wherever you live, you hopefully have access to internet. Obviously, there are places where that is not true, but by this point, we are starting to really seek out the opportunities to give people access to the internet, and there's clearly a large disjoint between people who can access it and people who cannot, and that's something that we as a society obviously need to work on. We have increasing ubiquity of high-speed wireless access. There's a big difference between needing to use your phone to access the internet and what we have today, where you can use any kind of device that you want, and when someone else picks up a phone, it doesn't cut off what you were downloading, that sort of thing. And we have the emergence of social networks, which can be good or bad depending on your perspective. This is, I think, a 2016 number, which is 1 billion users of Facebook. As of 2020, second quarter, there are 2.7 billion monthly active users, so this number has obviously skyrocketed, and we'll see if that number changes any more over time. But by this point, we have e-commerce, we have universities using the internet for all kinds of different things, like the video you are watching right now. Enterprises are running their services in the cloud, like Amazon, and we'll get to how all that stuff works in due time. Let's take a look at the structure of the internet and what it's like from a nuts and bolts point of view. So what's the internet look like? Well, we can see there's a lot of stuff here on the right side, so let's go through things one at a time here. So the internet is composed of billions of connected computing devices, which are called hosts or end systems. So you can think of your smartphone, your tablet, your wireless laptop, servers, PCs. These are the things that aren't running what you could call a backbone of the internet. These are the things that are using it so that they can talk to and hear from other devices. So all these are running network applications, and you can think of as the consumers of the internet if the internet was a big store. In addition, we have communication links. So these are things like fiber cables, copper, radio, satellite, the ways that you are able to, the medium through which you can actually transmit the information through the internet. And the transmission rate, the rate at which you can actually send this information, is called bandwidth. And finally, we have packet switches. These are what actually send the chunks of data, the packets, from one place to another, and so these include your routers and your switches. And you can sort of see how all of these are represented in the diagram over here, where you have your global internet service provider, which is basically a bunch of different packet switches, routers, switches, and so on. In addition to that, you can have regional ISPs, so these are just at different scales, and these are all connected to one packet switch or more on whatever network you're running things on. So if you're on a mobile network, this might be going directly to a tower, and the tower is sending out stuff to your laptop or to your PC that has a connector so you can get wireless internet, or to your automated vehicle, to a traffic light, any of these kinds of different things. And then in your home network, you might have your router plugged into one computer, and then that one computer is talking to your laptop and your other home stuff, that kind of thing. And then in an institution, you might have multiple different switches, and each of those also is communicating with different devices, and so on and so forth. The whole thing is a connected web of things, hence the name World Wide Web. So what we call the internet is essentially a network of networks. We have different like mobile networks, home networks, institutional networks. All these are interconnected in different ways. And then there are service providers who allow us the ability to communicate from one network to another one. And one of the ways that this is done is using protocols. This is sort of, you can think of this as and so a protocol refers to a system through which you can control behavior. And in this specific case, what we mean is the ability to send and receive messages. So you can think of when you're making a phone call, typically when you make a phone call and you pick up the phone, you say hello, because that's sort of the accepted standard through which you communicate. Is you say hello, the other person says, hi, this is my name, oh hi, I'm, like, one person's identity is usually known, and when you're done talking at the very end, you say bye, goodbye, the other person usually says goodbye as well, and you hang up. And so this sort of these protocols need to be agreed on by multiple different parties, so you all know the right way to send messages and receive messages. So some examples of some of these include TCP, IP, HTTP, these all end with a P because they're all protocols. Skype has its own protocol, and there's one called 802.11. So this is a set of internet standards, and it's specifically the 802.11 is the world's most widely used wireless computer networking standard. It's used probably in your home right now, as well as in different office networks, and it allows laptops and printers and smartphones and so on to talk to each other without needing actual wires. And you can see sort of a little diagram here where the only wire is up to the switch, and then everything that's actually on the network, all of these hosts don't actually need any wires because of this protocol that they all can agree, here's how we're going to talk with each other. Other kinds of internet standards include RFCs, requests for comments, which are managed by the Internet Engineering Task Force, IETF. And so these RFCs, requests for comments, are basically protocols or procedures, programs, concepts, also memos and just notes and silly things too, because internet people are silly. But these are really the standards that we all agree on when we are using the internet to communicate. And so this task force is the community, which essentially uses a rough consensus to decide how we should apply these RFCs to allow us to communicate via the internet. So you can break down the structure of the internet into different components, even just based on this diagram. What you can see on the outside, where you have the mobile network here, the home network here, the institutional network here, are all what you could call the network edge. So this is sort of the endpoints of the internet. These include hosts or end systems, which include clients and servers as well, places for hosting data, places for sending or using data. And some of these servers, I guess these can represent servers over here, are often located in data centers where they are not themselves the ones providing the internet, but they are the ones actually using it and being accessed by other end systems. In addition, you have access networks or physical media, so you can see these are sort of the lines that help you connect one device to another. And so these can be wired, they can be wireless, and they're the links in your communication chain. And then, so DSL is an example, cable, wireless LAN, LTE, all of these are different forms of access networks that you might use. And then finally we have the network core, so this is where you got the regional ISP over here, the global ISPs over here, internet service providers. And these are all just a series of interconnected routers, and this is where really the idea of the internet comes from, because it's a network of networks. No individual one of these switches connects to everything it needs to. Usually there is a path that takes you from one switch to another one, to another one, to another one, and eventually allowing you to sort of draw a line that connects wherever your one host is to the one that it needs to access. So how does a host actually send the data? Well, the host sending function takes an application message and then it breaks it down into smaller chunks. So if you have 1,000 bits that you have to send, you might only chop it up into 4 different packets, small chunks, that have 250 each, totaling the whole message at the end. So L bits, L is the number of bits in the packet itself, and using a access network, the host transmits that packet at a transmission rate, which is R, the rate at which it's transferred. And so this is the link transmission rate, also known as link capacity or the link bandwidth. These all mean basically the same thing. And that leads us to this little formula, which is how much time does it actually take to get this all sent. So the total packet transmission delay, which is the amount of time you need to transmit your L size bit into your link, is a pretty simple formula. If you have L bits that you need to send and you have a transmission rate of R bits per second, then you just do a division and you're left with how many seconds are left, L over R. A quick note on how we're using units in this course. Now normally you'd be using 1024 in terms of translating from, say, 1 byte to a kilobyte. It's 10,024 bytes for 1 kilobyte. But for this course we're going to keep things really simple. In terms of talking about bits to kilobits to megabits to gigabits, we're just going to use straight 1,000. So 1,000 bits is 1 kilobit, is 1,000 kilobits is 1 megabit, 1,000 megabits is 1 gigabit, just to keep things really simple and make our math a little bit easier. Let's take a look at the trip that a packet takes to go from one host to another. So it's going to need to go through a mesh of interconnected routers, and it might be forwarded by several of these before reaching its destination. So if I wanted to go from this top point over here all the way to the bottom, I need to go across and then over, down, down, across, over, and there needs to be a bunch of different steps that I take along the way. So what does this all look like? Well, on the left side here we have the packets themselves, so it's L bits per packet. Here's this little thing here is the source, is where we're starting from. The transmission rate that we're looking at is R bits per second, so we have that for this access link here. Here we have our router, we have another access link on the other side, and then we have our destination where we're trying to actually get our packet sent. So we're starting from the left over here, trying to send stuff onto the right over here. Now, what's going on along the way here? Well, it takes, like we just saw, L over R seconds to transmit our L size packet into our link, assuming that we have R bits per second. And here we're using a process called store and forward. So the idea here is that if you're sending a packet and it needs to all come in one little nice package that fits all the data you need, you can't immediately just start sending out the data of that packet the instant that it arrives at the switch. You need the whole packet to arrive. So what this means is that you need to consider the time it takes to send your packet from the source to the router here, that's L over R, and then you need to do it again because you need the whole thing to get loaded up into the router in the middle, and then it needs to get sent another step along the way. So the end-to-end transmission delay, so this is just assuming all we care about is the time it takes to send from one to the other one, ignoring propagation delay, that's something we'll talk about in a bit. We have L over R descended across this line, L over R descended across this line, you add them together, 2 times L over R. So what happens when things don't work exactly perfectly the way we want them to? You'll see that sometimes the transmission rate of some of these isn't equal. It's not always the case that every single link between two different places has the same transmission rate. So we can see here we have an incoming transition rate coming from our source to the very first router, has 100 megabits per second, quite a fair bit. But the link coming out of the router is only 1.5 megabits per second. So you can see this might lead to a little bit of an issue. And this leads to queuing and loss. So if the arrival rate, in this case in bits of 100 megabits per second, exceeds the transmission rate, the rate at which things are leaving this router, then we're going to have some issues. First off, packets are going to start to queue up. So if you're only sending a really small message, this might be okay for you, because what might end up happening is, sure, a lot of stuff is coming into the router really fast, but if there's not too much that needs to be stored here, then you should end up being okay, even if the rate at which stuff is being sent out isn't very quick. But eventually at some point, this buffer, this queue of packets that needs to wait to be sent along this link, if this overflows, if this buffer fills up, then you're going to have packet loss. And you may have heard the term packet loss before, and this is where you're trying to send information at too quick of a rate. It can't fit in the buffer, it can't be remembered, so those packets just get tossed off to the side because there's nowhere to store them, and they still need all these other things to be sent before that packet can be handled. So an alternative approach to using packet switching is using what's called circuit switching. And the idea here is that you allocate resources between your source and your destination, reserved for any calls that you need to make between them. This means you have dedicated resources. There's no sharing here. You don't have to worry about what happens if two sources are sending through the exact same way. That doesn't end up happening. Instead, you have a circuit-like guaranteed performance. And this means that if you're not using that resource, well, then it's just idle and sitting there and kind of wasteful, so there's no sharing involved. This is commonly used in traditional telephone networks, and it's kind of where you get that trope of people in offices where they have to connect the wires from one spot to another spot, because they're literally creating a circuit that goes directly from one point to the other point, and the wires need to draw the little line that you can see here where we start from our source, we go straight through, we're taking this line here, and we end up at our destination at the end, and no one else is allowed to actually access this specific line that we're using here. So let's do a comparison of packet switching and circuit switching. In this example, we have a link that has a transmission rate of 1 megabit per second. Each user is going to take up 100 kilobits per second when they are active, when they're actually sending something, and for any given user, they're active 10% of the time. So with circuit switching, how many people can we use? Well, if each user needs to reserve 100 kilobits per second when they're active, then you can have 10 users. Remember, we're using the 1000 rate, so 10 people can use it at the same time, because 10 times 100 kilobits per second is 1 megabit per second. That's using up the entirety of the link. And we need to ensure that everybody has a reserved spot that they can use to send stuff to guarantee that it's the case. How about for packet switching? Well, with packet switching, technically there's no limit. You can have as many people using it as you want, because you don't have to worry about whether or not something is being shared. You can share as many of these links as you need to. Now, provided as long as fewer than 10 are active at the same time, you should be okay. Now, if people are only active 10% of the time, though, what's the probability that, let's say we have 35 people, what's the probability that for 35 people, 10 or fewer are using it at the same time? So that way, just like circuit switching, everybody can still transmit at the exact same rate that they need to. It turns out the probability that 10 or fewer people are using it with 35 total users is 99.96%, so you're pretty good most of the time. In the tutorial, you guys can do the calculation to figure out exactly where this number comes from. But in this case specifically, packet switching allows a lot more people to use this network. With circuit switching, we only had 10, and that's the absolute maximum. With packet switching, we can have 35 people using it, although obviously because they're only active 10% of the time, they don't have to be using it simultaneously. We can allow a lot more people to use the exact same link to get things going. So based on this, well, is packet switching just always going to be better? I mean, packet switching is pretty good when you have bursty data. If you're only sending data 10% of the time and you're sending all of it in that time, then you should be pretty good with packet switching versus circuit switching. Resource sharing allows you to have a lot more people using that network at the same time, and it's a lot simpler because you don't have to set up the direct connection from your source to your destination. However, there's still problems with this. It's possible for excessive congestion to happen. You can have packet delay, you can have packet loss if too many people are using it simultaneously. And you need protocols that assure you can reliably transfer that data without losing packets along the way. And this is where things like congestion control come into play. So an important design idea is that you need to consider when you're figuring out communications, do you need to have a reserved resource like circuit switching allows, or is it more important to have on-demand allocation to allow a greater number of people to access things? You might want to think of some real-life examples of which ones might be better for which. And there are some examples where circuit switching is something that we still use versus packet switching, which we do tend to focus on for certain networks, but there are definitely examples of each of these still being used in our current time. So I said that the internet is a network of networks, but what does that really look like? Well, here's a question to think about. If you have millions of different access nets and you need them all to be able to talk to each other so that my computer here can talk to your computer wherever it is, how do you connect all these things together? Well, the really simple, easy option is you connect every access net to every other access net. So this one's connected to all these ones, that one's connected to all these ones, and so on and so forth. And then your end result is that you're not going to be able to scale this too well because you need O of n squared connections. That's a pretty big number that you're going to need. Not really the best way to do things. Another option you can have is you connect all your access nets to one single global transit internet service provider, and it has an agreement with customers in order to, like an economic agreement to make sure that, okay, I'll be set up here and I'll make sure that all of these messages get sent out to everything. So now everybody's relying on this one internet service provider to communicate from their access net to another one. Well, undoubtedly what's going to result from this is that if that's a viable business, then there's going to be some competitors who also want to do the same thing, and they create their own little internet service provider business where they connect different access nets, and now you're not all relying on the same access net anymore. So now you have another problem of what if my access net over here on the left side needs to talk to this one over here on the right side, and I don't have a link to them anymore. Which means now there needs to be an interconnection between these different internet service providers so that your access net here can talk to this access net here. So there are a couple ways you can connect things. One is through what's called peering links. This is just a direct connection from one internet service provider to the other, and so if packets are being sent, say, from the left to the right, then once packets are sent over from here to here, then internet service provider C gives over the permission to internet service provider B to handle the rest of the delivery. And you also might have these points here, which are called internet exchange points. Sorry, I'm in the way. Internet exchange points, which are physical locations, which don't actually provide any internet capability themselves, but they allow you to transfer data from one point to another one. And in addition, you end up having regional networks, which might arise to help you if you just want to connect two really nearby access nets. So if you have this one over here and this one over here, in order to make it so you don't need to rely on this giant global ISP, you can just deal with this little tiny network, which means that you don't have to travel so far to get from one place to another. And in addition to that, we have content provider works. So you have things like Google services and Microsoft or Netflix, which all want to run their own networks, which bring their services directly from their servers to the user as well. And they might want to avoid using some of these internet service providers if possible. Otherwise, they're sort of bottlenecked by another company, which is not what they would want things to be like. So in the end, what this looks like, and I'll move myself a little bit again, is this internet structure, which is sort of a tiered approach to how networks work. So at the very top here, you have your global internet service providers. This is called Tier 1. Some of these include Sprint, AT&T, NTT. These provide national and international coverage. So this is how my computer here can talk to yours if you're in China or Europe or wherever else. You obviously have these internet exchange points, the physical locations that allow you to connect from your Tier 1 provider all the way to your access nets. And you also have Tier 2, which is where you have your regional ISPs and so on. And so at the very center, you have a small number of well-connected networks, which is where these are happening. And you also may have a content provider network. So something like Google might want to only be connecting its data centers to the internet bypassing these tier 1 ISPs, and so it usually will try to set up its own little way that it can connect to these internet exchange points to directly reach you, the customer, without needing to, say, have Netflix deal with Sprint every time it wants to send you a movie. So before I went through a brief example of how packet loss works, let's go through a bit more of the details of exactly what's happening here. So how do loss and delay occur when you're sending information through packets? Packets queue up in these router buffers, and this happens any time that the arrival wait to this link exceeds the output capacity. If that's the case, where the things that are coming out from here are slower than things coming in, then things need to queue and they need to wait for their turn. And this causes a number of different delays to happen. So the packet being transmitted has a delay, the packets queuing up have their own delay, and if there aren't enough places to actually store all these packets, we have loss. This is where a packet arrives at the router, there's not enough place to actually store it, so it just gets thrown out because it can't be held onto. And there's 4 different sources of packet delay. So we have propagation, transmission, queuing, and nodal processing. So let's go through each of these one at a time. So the total delay of everything happening at this node, this router, is the sum of all these other delays. So you have to add them all up, and that's the total delay that happens by processing everything from here going across. So starting with our nodal processing, the delay here comes from the need to check to make sure there aren't any errors, make sure the packet isn't actually broken when it arrives, there wasn't some number that got switched along the way, which can happen, to make sure that you figured out where the output link actually is, figure out how to actually send it, and usually this is in terms of units less than milliseconds. So this could be significant, could be not, depends on what you're sending. Then next we have queuing delay, so this is the time it takes to actually wait at the little link for everything else to go by, and this is entirely dependent on the congestion at the router. If you're the only person sending stuff through, it might be not too significant, but if 35 different people are using something on a network that's only intended for 10, then you obviously are going to have some kind of queuing delay happen. Next up we have transmission delay, so this is what we went through before. We're just looking at the packet length divided by the link bandwidth. You can think of this kind of as the width of the channel that's used to send these packets along. If you have a lot of bandwidth, then you can send things a little bit quicker, as opposed to if you have a very limited amount of bandwidth, it's going to take more time. And then finally you have propagation delay, and this is the length of the actual physical link that you need to send stuff. So if you have a wire that you need to transmit data through, there is an actual physical time it takes for you to travel through. And so this is a propagation speed of typically 2 times 10 to the 8th meters per second. So this is a number that you can reference later. And literally the delay is just the length divided by speed. That's it. Now some of these delays are significantly different from each other, and we can go through an analogy of a caravan of cars to sort of illustrate what it's like to have packets going through a network. So these cars travel through the distance that they need to travel at 100 kilometers per hour. Let's suppose that we have toll booths along the way that take 12 seconds to service the car. So this is equivalent to the transmission time. So you can think of each car as a bit, and the whole caravan, the list of all these bits, is a single packet. And if we have the question, well, how long until the caravan is lined up at the second toll booth, and it makes it all the way from where it starts across until it's being queued up over here. Well, the time it takes to push this whole caravan through the toll booth is, well, 12 seconds times there's 10 cars that have to go through, so it's 120 seconds. What's the time it takes for the final car to go from the first spot onto the second spot? Well, it's 100 kilometers, seems to be this distance here. The speed that they travel at is 100 kilometers per hour, so the total is 1 hour. Makes sense. So the total time that you need to answer the question is, well, 120 seconds is 2 minutes, 1 hour is 60 minutes, so its total is 62 minutes to do the whole thing. We need to travel the whole distance, plus include the delay that we have at the little toll booth. Now, in this case, it's very clear that one of these is significantly different from the other. So you can think of the pushing, the getting all these guys to figure out their business at the toll booth as the transmission time, whereas the propagation here, the propagation delay, took a lot more time. If you compare like 2 minutes versus 60 minutes, it's a pretty significant difference. So we usually refer to one of these delays as a bottleneck if it's significantly more than the other kinds of delays that are here. If the time that it took to push this through the toll booth was say 5 hours, and that's the delay we would probably want to focus on if we wanted to improve the speed of this network. Now, let's suppose we upgrade our little cars, and instead they move at 1,000 kilometers per hour. And suppose that the toll booth now takes 1 minute to service a car instead of 12 seconds from before. So here's a question. Will cars arrive at the second booth before all of them have been serviced at the first one? Well, the answer is yes. So after 7 minutes, the first car, which needs to get serviced at the toll booth and then speed its way along over here, that first car will arrive. And at that time, there will still be 3 other cars here at this original booth because they have to wait for 1 minute for the first one, 1 minute for the second one, 1 minute for the third one. So only 7 of them get processed by the time that the first one speeds its way through the 100 kilometers here, going 100 kilometers per hour. And if you do the math here, so it's 1,000 kilometers per hour that is its speed, which means it's going to take 6 minutes to go 100 kilometers, and plus 1 minute to do the servicing, so that's 7 minutes total. So after that 7 minutes, first car has reached the second toll booth, and if 7 minutes have gone by, then of these 10 cars, only 7 of them have been serviced, meaning 3 are left. So this means now the transmission is the bottleneck. This process here of things waiting at the toll booth is now our bigger concern, because now the delay doesn't come, the most significant delay doesn't come from us speeding through this whole thing here. It comes from the fact that we need to process everything. And once the car has reached the toll booth, if you remember from before, you have to wait for the whole packet to arrive before you can start servicing things. So that means there's going to be a delay here where this thing is just sitting here waiting for the rest of the packet to show up. So if we have delays happening where queuing is going on, what exactly does that look like? Well, there are 3 variables we need to consider here. First off is the link bandwidth, second is the packet length, and then finally is the arrival rate of the packets to whatever link that we're at. So let's suppose that the packet length times the arrival of these packets divided by the link bandwidth is about 0. Then pretty much there's no real queuing delay. Things are just moving along smoothly without too much of a problem. Let's suppose that it's approaching 1. So they're becoming pretty similar. Then the queuing delay is going to be pretty big. As we have stuff coming through, we still have a bandwidth that can barely manage the ability to actually send everything at that same rate. So there's going to be more of a queuing delay there. And then finally, what happens if the arrival rate times the length of the packets is greater than the link bandwidth, which means the ratio is greater than 1. Well, then what ends up happening is there's more work arriving than can actually be serviced. So the delay can potentially be infinite, where you just have something sitting there, nothing is going on because you have such a huge delay happening. So if you want another car analogy, when things are about 0, you have an empty highway. When stuff is approaching 1, you got a packed highway. At least things are still moving, but at least there isn't a pileup like there could be. That would be much worse. So when does packet loss occur? When you are queuing, buffering, in a preceding link, there's a finite amount of capacity in which you can actually store different packets. If you have a full queue when you arrive at the buffer with any given packet, then it's going to be dropped, it's going to be lost. What happens with this lost packet? There's a couple options of things that can happen. First off, the previous node, for example, here we're just going directly from our source to our first switch and then across. If it realizes that one of those packets was dropped, it might just need to send it again. And then hopefully by that time this buffer will have had time to send things through, and there will be an actual space that it can wait in the queue for storing to be sent later. If this isn't the source, and let's suppose this was one switch sending things to another switch, then it might be the case that the switch needs to send that again. But this depends obviously on what what link you were looking at in the system. It might be the case that you need to go all the way back to the starting point to send that packet another time. Another possibility is just you don't do anything, and this might happen, for instance, for some types of information that you send where you don't need to guarantee that every single packet makes it there, as long as most of them do. So what is throughput? Throughput is a rate, so bits per time, at which bits are sent between a sender and a receiver, a server and a client. And you can look at this in two different ways. You can look at an instantaneous throughput, which is just a direct individual rate at any given point in time, or you can look at the average rate over a longer period of time. So here we have a server that has f bits to send in a file, calling it f, that it sends to its client, and it has two links that it needs to send things to. The first one has an instantaneous throughput of rs bits per second. The second one has rc bits per second, and obviously these don't need to be the same. Another way you can think of this with an analogy is your bits can be fluid, and suppose you're sending this fluid through a pipe. And this is a thinner pipe, so it can't carry fluid at the same rate as this larger one over here. So the average throughput is going to be going to change based on the fact that one of these pipes is bigger than the other one. Now, what is the average end-to-end throughput for two different scenarios? You might have one scenario where RS is smaller than RC, and you might have the opposite where RC is smaller than RS. And what ends up happening here is that you have what's called a bottleneck link. One of these links is going to have a constraint on your end-to-end throughput. Because of how small it is. You can imagine that there might often be more than just these two links here. If there's going to be 100 of them, but one of them is so teeny tiny that it delays everything that's going on, then your average end-to-end throughput doesn't really depend at all on these larger links, the ones that have a higher rate. It really is dependent on what is the bottleneck one that actually stifles your ability to send things at the quickest rate possible. Let's talk about layers of protocol in the internet. So networks are pretty complicated. There's a lot of different pieces going on. We have our hosts, our end systems, our routers, links of various kinds of media, applications, protocols, hardware and software. How do we organize all of this? Is there any way that we can actually structure at least our discussion of networks? Well, there is. Let's give an example just to show kind of one way that you can do things, and it is analogous to the way that we actually are going to talk about networks in this course. Let's describe the organization of a whole air travel system in an organized way. So everything from going to the airport to landing at your destination. So one step at a time. First off, you begin, if you're going to need to buy your ticket. That's usually the first thing you need to worry about. After that, you're going to, when you go to the airport, you get your baggage checked. You have your ticket already. That's been taken care of. Once your baggage is checked, you head over to the gates. You load up onto the plane. So your baggage has already been checked. You got your ticket. You get on the plane. Now that you're on the plane needs to do a takeoff. It starts going. It gets faster. Goes into the air. Then we have airplane routing, so hopefully the person flying your plane knows what they're doing. They travel, they make sure the plane goes the way it needs to go, they route it, they travel the plane where it needs to go, and then you land on the runway at your destination where you want things to be. Now that you've arrived there, you step out of the plane, you head over to the gates, you exit the plane essentially, entering the airport. Now that you're in the airport, you can go and claim your baggage. It's been hopefully brought there on time for you, and you hopefully didn't lose it, otherwise, sorry. And then lastly, you complain about the ticket because it was a terrible flight and you would never ever fly with that airline again. Yeah, okay, so there's a series of steps. Now, you can break this down into different layers. So if you look at it, the first thing we do is buy our ticket, and the last thing we do is complain about our ticket. All of that is ticket-related things, so you can categorize that as a service that relates specifically to tickets. Similarly, we checked in our baggage and then picked it up later, so all of that is something that you can categorize under baggage. Entering the gate, exiting the gate, those are all gate-related things. Takeoff and landing are all on the runway, so you can group all that together, and then all the routing happened all at the same time as well. So each of these layers implements its own service via its own internal actions, the things it is doing by itself, and it relies on the services from the layer below. Your baggage getting there really depends on you being able to, and you picking up your baggage depends on you being able to get into the gates, have the plane take off, have the plane go the way it's supposed to be going, and then return to the baggage claim area to actually pick it up. So there is sort of an implicit assumption that if you're going to be able to claim your baggage, that's because everything, all the steps between that and when you checked it in, all worked correctly. And each of these relies on everything below it to work properly, otherwise it doesn't really make a lot of sense. It's kind of hard to land on the runway at your destination if you weren't able to route your airplane to the right destination in the first place. So why do we use layering? Well, when we're dealing with a complex system like the internet, using an explicit structure allows us to identify and relate the different pieces of the system together. And so this layered reference model allows us to discuss the different components that are interacting with each other for the purpose of the network. In addition, modularization makes it a little bit easier to maintain these things. Let's suppose that you wanted to change the gate procedure. That way you don't have to fix the entire rest of the system because you only have to focus on that one specific component that you're worried about, which is maybe the gates don't work properly. And that way, if you do need to make changes, that's ignored by the rest of the system. How you fix the gates doesn't impact how the plane is being routed. So let's break down the 5 different layers of Internet protocol in the Internet protocol stack. At the very top, we have the application layer. So this is where the actual applications are happening. We have our HTTP, our websites, our simple mail transfer, file transfer, all that is happening at the application layer. Then we have the transport layer. This is where process-to-process data transfer is actually happening. So things like TCP is allowing us to actually send the information from our application via the transport layer. After the transport layer, we have the network layer. This is where we take datagrams, which are essentially taking information from these top two, and figuring out how to route it from our source to our destination. And this is where IP comes into play, where routing protocols come into play. All of that relies on an understanding of the network layer. After this, we have the link layers. This is the transfer directly between neighboring network elements from one switch to another, using the Wi-Fi, using Ethernet, and so on. And then finally, you have, I'll move myself slightly so you can see, the physical layer, which is literally the bits themselves on the wire. So how do we handle encapsulation using this layered approach? Well, at the very source, where we have everything starting out, we have a message from our application layer, a segment from our transport layer, a datagram from our network layer, and a frame from our link layer. And as we build these up, you can see how each component of the one above it is held by the one underneath. So the message we have here, M, is contained in this segment built from the transport layer. Both of those are held by the datagram, and all of that is held by the frame. And the frame is the thing that gets actually sent by the physical layer to the switch at the next stage. And so as we send through the physical layer, this whole thing gets processed through the link layer because right now we're on a switch. So this little chunk here, which contains all the information we need, continues on through the switch to the next place. Then we reach a router. The router needs to tell us where things are actually going to be going. So here we use one of the parts of our frame to figure out where that's going to be. We go through our network and then follow the link again and through our physical layer all the way to our destination. And so as all of this is happening, each of these layers doesn't actually understand what's happening with the layer next to it. All that's happening is it's built a structure that allows it to contain the information it needs to carry along the way, such that whatever is in this message, the segments, datagrams, frames, they don't care. They just see, oh, here is data, it needs to go to the right place. Well, transport layer will tell me things like, here is the application that's going to need to receive this message. The datagram will say, okay, here is the path that I need to send these things through, and the frame will contain the whole entirety of the packet that we're actually sending through the physical layer. So when we arrive at our switch, we have our frame, and the frame needs to go to the next place, and so the switch sends it along. When we get to the router, well, it needs to actually access information through the network layer, so it considers only these 3 parts that are in here and uses the information in that first part to continue on. And so the M here is for message, and these H's, which are H sub T for transport, H sub N for network, H sub L for link are all headers, and so the only information that's in them isn't data other than what's needed by that layer to get things working. So it might be something like the IP address of where you need to go might be in one of the headers that you're looking at. But most important of all is that none of these headers need to actually know what's contained in the rest of them. They're all working independently to get your message from your source to your destination.